Here we are back again, this time to look at solving radical equations. We're going to combine what we know about radicals and equations. We'll do a little warm-up here with simplifying some expressions. We should be able to do this calling on things we have learned previously. I can divide this up. Remember, this is the power, and this is, this is the root. When we're looking at a rational exponent, the numerator is the power we're applying, and the denominator is the root. So I could write this as 25 to the 1/2 power, which is saying root 2, and the power of 3 on the outside. Well, the 1/2 power of 25 is the same as saying what? That's right, the square root of 25. We have to remember that we're going to raise that to the 3rd power after we figure out what this is. It's not hard to figure out, is it? This is 5 raised to the 3rd power, which at this point many of you are going to remember is 125. And if you don't remember it, what can you do? Say 5 times 5, that's 5 squared, times another 5 would give you 5 to the 3rd power. So you can figure it out. Let's try this one. This one is, let's try writing it with a radical, with a rational exponent. So we'll say 8. We're going to put the power in the numerator, and the power is 2. We're going to put the root, that index, in the denominator. And I'm going to rewrite that with 8 to the 1/3 inside my parentheses, and then put the power of 2 on the outside. That's the 3rd root of 8, and we all know that at this point. That's 2, and 2 squared will give us 4. These are kind of fun to do, and they're really good warm-up for what we're about to do. Let's try this one. This one's one that you could easily get mixed up on, because you have to think very carefully about how you apply this. You're going to distribute that power of 4 to the variable and also to the coefficient. So we're actually going to end up with 3 to the 4th power and a to the what power? A to the 8th power. We wouldn't leave it with 3 to the 4th power. My goodness, what is 3 times 3 times 3 times 3? You can pause this for a minute while you figure it out. 81 a to the 8th power. Pretty good. Now this one, we have a lot going on here. We've got the 1/3 power, which is really saying the 3rd root. That's going to apply to the variable and also to the coefficient. So we're going to have 8 to the 1/3 power, and we're going to have x to the 3rd power to the 1/3. When we put it together like that, we've got the root in the denominator and the power in the numerator, and we know that would simplify. I'm not touching this 8 to the 1/3, although I know you're probably telling me right now what that should be. But this would be 3 over 3 is the same as the first power, which we never bother writing. That's what things ordinarily are to the first power. And the third root of 8 we know is 2. So this simplifies very nicely, doesn't it? 2x. Yikes, what am I looking at here? Okay, let's see what we can do with this. We're going to use rational exponents to try and help ourselves out. And we'll first do this expression, and then we'll do this expression. We've got a, and it's got the root 3, so we put that in the denominator, and a power of 2. This, the whole thing, and let's put it into parentheses, 8a. What's the power on this? This is a power of 1, and this is a power of 1, and it's not written. And it's a root of 3, so this is to the 1/3. I'm going to leave the a alone for a moment. So we've got a to the 2/3. And then we're going to take this 1/3, we're going to distribute it to the 8 and to the a. So I'm going to end up with 8 to the 1/3. And yes, I hear you. I know what that is. We'll just wait a minute before I write it down. And this would be a to the, oops, come on, 1/3. Let's keep going with this. It's getting exciting now. This right here is the same as 2, so we might as well just go ahead and write it as 2. Then I've got, if I could look at this just a little differently, I've got a squared to the 1/3, and I've got a to the 1/3, right? And that's a to the first power and 1/3. Now maybe you see an easier way to have done this, and we're going to talk about that in just a minute. If they're both to the 1/3 power, then I could say 2, and they're both to the 1/3 power, so I'm going to put that outside the parentheses. And I've got a squared times a, and of course we know it's the first power, which is the same as 2a to the 3rd to the 1/3 power. 2, you put the a as the base. We've got 3 as the power. 3 is the root. It's the same as 2a to the first, and we don't bother writing that. And I think I heard you out there telling me something a few minutes ago. I'm going to extend this page because you probably remembered that as long as you have the same base, you've got two exponential expressions with the same base, they're being multiplied together, what do? You simply add the exponents. So wouldn't it have been easier, should have done this, I'm sorry, wouldn't it have been easier to say base A, and we'd say the 2/3 plus the 1/3, and see where that's coming from up here and here. If we add 2/3 and 1/3, what do we get? Of course, 3/3. Oops, I can't forget the A, that's the base. My goodness. So that might be a little quicker way to get there. But whichever way you're thinking about it, we get to the same answer. It's very nice mathematics. The rules, as long as we follow them, will get us to the right place. We can get started now with talking about radical equations. We're going to start by talking about some equations which do not have radicals in them, just to see if we understand how all of this works. If A is equal to B, so both equal to the exactly the same, if I square both of them, will they still be equal? Can you think of any number where that wouldn't be true? The thing to do here is to maybe consider a negative. Would a negative work? Does 0 work? Does a positive number work? You can't think of any where that doesn't work. So we're going to say yes. If A equals B, A squared definitely equals B squared. However, there is something a little trickier down here. If A squared equals B squared, it is not true that A necessarily equals B. And can you think of an example where that would happen? Well, if A were equal to 3 and B were equal to -3, then we know that A does not equal B. Yet look what happens when I square it. I take A and square it, which is 3 squared, and I take B, which was a -3, and square it, and I've got 9 equals 9. So I can have a situation where A squared equals B squared, but this is not true. No. The principle of powers. Let's see what that's all about. Let me see if I can select this here. So I need a different tool for that. I want to reveal that to you, the principle of powers. For any number, any natural number, let me erase those dots, get them out of the way. For any natural number n, if A equals B, then A raised to the same power as B is raised to will always be true. That's going to turn out to be very handy for us when we start trying to solve equations. Okay, equivalent equations have the same solution sets. We know this. We have talked about this previously. The problem we're going to run into with radical equations, I don't think we've seen this before. We're going to have to watch out for something called extraneous roots. What happens with extraneous roots? You follow the rules like you're supposed to, and you get a solution, but then when you try the solution to see if it works, it doesn't. So if you get a solution, you're going to have to check it and see if it will work for you. So we're going to try to solve this equation here. We've got the square root of A, and with all radical equations, we're going to try to isolate this. Right now, it has a 2 added to it. We're going to do the opposite operation to get the square root of A by itself. We'll subtract 2 from both sides. We'll have the square root of A is equal to 5. So what must A be? Well, we're going to square both of these. We square both sides. If we square a square root, we'll get what was the radicand, an A, equals 25. Okay. So we're going to check this now. And when we check for extraneous roots, when we do this check here, we always go back to the original equation. That's the only way you can check it legitimately. So if A is equal to 25, we're going to say the square root of 25 plus 2. That's one side of the equation. The other side was 7. What is the square root of 25? It's 5. Hey, notice, please, we're talking about a positive square root, right? So it's 5 plus 2. We don't have to go any further. We know that works. That's good. Let's try another one. Now, these are going to get more complicated as we go, but we've still got an x we're trying to solve for. We use the same principle always. We try to get all our x's on one side of the equation. Right now, I've got 3 square roots of x on this side and 2 square roots of x on the other side. I want them both on the same side, so I'm going to subtract 2 square roots of x from both sides. And when I do that, I'll be left with 1 square root of x equals a negative 1. What's my next step? Well, I want to know what x is. I'm not interested in what the square root of x is. So I'm going to release it from its square root by squaring, and that means I have to square both sides. Now I'll have x equals, I square a negative 1, I get 1. Let's check it. 3, and if x is equal to 1, I'm talking about the square root of 1. And on this side of the equation, I've got 2 square root of 1 minus 1. I'm just going to pause for a moment to point out to you that, look at this. When we're checking, we're using our original equation. Okay, the square root of 1 is going to be 1, so this turns out to be 3. The square root of 1 times 2 minus 1. Uh-oh. Doesn't work, does it? So this was our first example of an extraneous solution. We used all the correct logic to find it, but it doesn't work because we know that 3 is not equal to 1. So, no, this one didn't work. When you do these problems, if you do not check for the extraneous solutions, you haven't finished your work. I know in the past we haven't always had to go back and check, but with radical equation, it's imperative that you check. Oh, this looks very complicated to me. The reason I'm saying that is I've got x I'm trying to solve for here and another x over here. We want them both on the same side of the equation. Yikes! And as if that's not bad enough, this one's trapped in a radical. Oh, I'm having to brainstorm. Sure, this is a square root. So how can we release it? We just square it. Only trouble is, this is going to get a little bit messy, we have to square both sides. You can't square one side and not the other. Now, you can take a moment and figure out what this would be. We are squaring a binomial. You know that pattern, or you can write it out as these two binomials and FIFO it. I mean, FOIL it. I'm sorry, FOIL it. So on that side of the equation, when I multiply everything out, that's what I get. On this side, it's much simpler because the power of 2 and the root of 2 cancel each other out, and I have 18, just the radicand, all by itself. It is a bare naked radicand now. Radicals all gone. I want, ooh-wee, look at this. I've got a quadratic. Remember, anytime you see a quadratic, I want you to think of this. The 0. I can hear you saying it. I love this because its name tells you exactly what you have to do next. Zero product property. I got a little carried away with the product. Whoops, but it didn't get its T. So zero product property, which means I need a 0 on this side, which I obviously haven't got. So I'm going to subtract 18 and add 2x to this side, which means I must do the same thing over here. I'm going to add 2x and subtract 18. I'm just lining it up underneath where it's actually going to be added, make it a little easier. Then I get x squared. This will be minus 8x, and this will be plus 7. Good, I've got the 0 I needed. The other thing I need is the product. Right now I have a sum. I have a trinomial, but we know that quadratic trinomials very often will factor, then I'd have a product. Let's see if this one will factor for us. We don't have to think too much about the x squared. We know that's got to be x times x here. Now we have to think of two factors of 7 that when we add them together will give us a negative 8. So you tell me. That's right. Now we can do the mini equations. We've got x minus 1 equals 0. And we've got x minus 7, it's a minus, equals 0. So we've got two possibilities here now. X is equal to 1. X is equal to 7. Both of them positive. You notice I have taken the equation we've been working with, and I've got two places to check it. Right there and right there. That's because I already knew we were going to come up with two possible answers. We're going to check each one of them. So we'll check the 1 first, and we'll say 1 for x minus 5. And then we've got the square root of 18 minus 2x. That's going to be the square root of 18 minus 2, isn't it? Because 2 times 1 is simply 2. So over here I'm going to have a negative 4. And here I'm going to have the square root of 16, a negative 4, and a positive 4. This does not work. This one is extraneous. Well, let's try the 7, see if that one works. We're going to have 7 minus 5, and then we'll have the square root of 18 minus 2 times 7, or, that's right, 14. When I do this, what do I get? Yes, of course, 2. And here I've got the square root of 4. This is a happy one. That one worked. So we solved it. We got two possible solutions. We checked them. And this one was extraneous, but this one was just fine. So that would be our answer. What do you think? It's kind of easier than some of the other stuff we've been doing, isn't it? Solving radical equations. Oh my goodness. To have two radicals on the same side of the equation is a nightmare. We shouldn't have that. That's not going to work out well. So I know I've told you we should try to keep the variable all on one side. But if I start squaring this, what's going to happen? This will get released. This will get released, but we'll have an ugly middle term. I'm thinking that it might be a little easier if I actually subtract this radical from both sides before I start squaring things. I'm not sure that actually is going to make things easier, but let's do it that way. So I've got the square root of 3x plus 3 equals 5 minus the square root of x plus 2. Well, you know, it might not have been all that much of an advantage to do that, because either way we're going to have a middle term with a radical in it. This one is going to work out very nicely. Square root and power of 2, I'll have 3x plus 3. But over here, I have a middle term. I'm going to have 25, and this is going to be x plus 2. That radicand is going to be released, but I'll have a middle term of negative 10 square roots of x plus 2 plus this. So I'm not sure I saved myself very much. Let's subtract 25 and subtract x plus 2 from both sides. I did it to one side, we have to do it to this side too. And I'm going to subtract an x and subtract a 2. You see why I did that? Because when this gets distributed, I'll have a negative x and a negative 2. Alright, so let me go through all of this. I've got a 3x and I'm subtracting x, gives me a 2x. I've got a negative 27 and a positive 3, so I'll have a negative 24. On this one, this will 0. This will 0. And I've got 10, actually a negative 10, square roots of x plus 2. I am in better shape now. I had 2 radicals. Now, by squaring both sides, I've got myself down to 1. I want to get this radical all by itself so I can square it most easily. I could square the whole thing right now, couldn't I? Why don't I just square that? That will give me 4x squared. I'm going to have a middle term. Let's see, 24 times 24. What's that going to be? I should extend this page just a moment. Um, 48. $5.76. Okay, yikes, that's a ugly looking thing. Okay, plus 5.76, and I'm going to have a middle term here of 2x times negative 24, or negative 48x twice, which would be negative 96x, equals, when I square a negative 10, what's going to happen to it? Negative 10 times negative 10, I'm going to have 100. And when I, oops, I should have a square there. And when I square this, I'll have x plus 2. 4x squared minus 96x plus 576 equals, now I'm going to distribute this 100. Now you can pause at any time, because I can imagine that this one you'd like to take a breather. So I'm going to subtract. Remember, we want to use the, when we've got a quadratic, we want to use the zero product property. I have a hard time with those t's. So I'm going to subtract 100x, and I'm going to subtract 200 from both sides. Subtract 200, subtract 100x. I'm definitely going to have to extend the page. So after I do that, I'm going to write my answer right down here. I've got 4x squared minus 196x plus 376 equals 0. At this point, I've got the 0 that I need, and I could think about the product. One of the things that I'm noticing is that all of these are even numbers, which tells me I can at least divide them by 2, and maybe I can divide them all by 4. I'm going to try that first to see if I can divide this whole thing by 4. 0 divided by 4 will give me 0. 4x squared divided by 4 will give me x squared. 196 divided by 4 will give me, and of course it's a negative, 49x. And if I divide this by 4, I get 994. Now, check me and make sure I haven't made any mistakes here. Now I'm looking to factor this because I want to get the product we need. We know it's going to be x and x. What else do we know? I've got to have two factors of 94 that when I add them together will give me 49. I'm definitely extending this page again. Two factors of 94. Well, let's think about what factors I might have for 94. 94. If it were 2 times what would give me 94? 47, right? Oh my goodness, that's it. Well, I'm lucky I hit it the first time. So if I had a negative 2 and a negative 47, that would be negative 49. So that's what it is. It's negative 2 and negative 47. So if I do my little equations, x minus 2 equals 0, x minus 47 equals 0, I get x is either 2 or x is 47. Let me get back up here. So we know we've got to look at either 2 or 47. So let's try them out. So I'm going to do the square root of, we're going to try 2 first. 2 times 3 is 6 plus 3. And square root of 2 plus 2, and that would be the square root of 9 plus the square root of 4, 3 plus 2. Nice! Okay, so we know that one of our answers, where in the world am I going to put it? It's terribly busy here. I'm going to say, okay, we know this. X, we checked it, it works. X equals 2. That's a good solution. The other one was 47. 3 times 47. Somebody do that for me, please. I can do the 47 plus 2. That's easy enough, right? 49. So what was that? 47 times 3. Did I do that right? 47 times 3. Yeah, guess so. Okay, so 141 plus 3. Oh, this works out actually to a perfect square. That's very nice. The square root of 144 and the square root of 49. Oh, but there's no way that's going to equal 5. No way. No, that was extraneous. What a problem. What a problem. We're going to look at one more, the volume of a sphere. This is one that you learned in geometry. Perhaps you remember it. 4/3 of pi r squared. We're going to solve for r. All right. So that would be right here. Right now, it's being multiplied by 4/3. So we're going to multiply by the reciprocal. And of course, what we do to one side of an equation, we do also to the other side. So we'll be able to say, I'm just going to take this side and write it first. Pi r cubed equals, see what's going to happen here? Oops. Forget that. Let me go back. Sorry. We want to solve for r. And I put the wrong thing in, didn't I? It should have been the reciprocal of that. I said it, but then I didn't write it. It'd be 3/4 on this side and 3/4 on the other side. Now I'm going to simplify this. So that's 1. And I'm just going to take this side. Pi r3. And it's going to be equal to 3v over 4. What else do we notice? This is being multiplied by pi. So to isolate the r, we're going to divide both sides by pi. This will become 1. And I'll have r cubed is equal to 3v divided by 4 pi. I don't want to know what r cubed is, though. I want just what r is. So I'm going to take the cube root of that. And you know what I do to one side, I have to do to the other. So here's my r. We said we were going to solve for r. Here it is. It's not very pretty. Now it says find the radius, and that's what the r is, of a sphere with a volume of 905 cubic centimeters. So the radius would be the cube root of 3 times 905 centimeters. Well, let's do it right here. That'd be 15. You, I hope, will use your calculator for this. 3 times 9 is 27. So it's 27 over 15. Oops, this should be a cube root, right? Come on. Why isn't it writing? And it would be centimeters. We probably would want to figure out what the decimal is, but you know what? We have already been at this for 40 minutes. That's the end. I will see you in class.